We stopped here last time. We were talking about we are talking about the welding. We stopped here last time about the weld quality. Weld quality, when you say that the weld quality, it means that the concern to obtain an acceptable weld joint without defect. Weld joint, acceptable weld joint without defect. Without defect mean weld is good quality, right? If you have a defect, this one affecting the quality of the weld, right? A topic we're going to discuss here, residual stress and distortion, welding defect, and the inspection and testing methods. This is the item that we're going to discuss here. Okay, residual stress and issue actually. It is a thermal residual stress because you do heating and cooling, but not only heating and cooling. This is not for all material, but heating and cooling localized heat because you do heating in exactly in a weld zone, not all the part, right? You heating and cooling exactly in certain locations. So residual stress increase in this area or thermal residual stress increase in this area, and this one cause distortion and warping in the part, because this is mainly because heat is very localized, melting based material in this region or in the welding exactly in the welding region, and this one the leading to distortion as you can see here. So because of here you heating and melting exactly in certain location, not everywhere, but exactly in certain location, very localized heating and melting and solidification in these areas, and you expect that you get a high residual stress, very high residual stress or thermal residual stress exactly in this location while solidification done. Distortion usually happen, different type of distortion. This kind of distortion happen in the welding, different type of distortion actually happen in the welding as you can see. This actually is not good. We would like to solve this problem. We don't want to have distortion. Actually, it is undesired. If we can eliminate, if we can minimize, if we can eliminate this distortion, it will be better. So how to do? There are some techniques actually. There are some techniques to minimize this distortion. The following technique can be used to reduce warping in arc welding. For example, first, welding fixture. Use a welding fixture like this. Welding fixture to not allow the distortion happen. So is this one a rigid fixture to hold the part together, so later this one can be prevented. Other also whatever we call heat sink. This is a heat sink. You increase actually the surface area. Heat sink, this heat sink we added to the weld. I mean, we use the heat sink and added the weld or do the weld above the heat sink. What will happen? Heat sink absorb heat quickly and dissipate quickly because you increase the surface area. And you know when you increase the surface area, what will happen? Increase surface area, it means that the heat time will be very very short, then quickly dissipate the heat, allowing that the material to not that much distort. So rapid move heat from the section of the weld part to reduce the distortion, so we call it heat sink. So either you can do the fixture, you can use the heat sink, you can use whatever we call tack welding. This is a tack welding, several tack welding here. Initially, you do tack welding, which is a multiple point, a long joint can be created. Here, you create this tack weld, several point initially before you do the welding. Then later you do the welding. What will happen? This kind of tack weld or this kind of weld point that you apply make this one rigid. Later, when you apply the weld done here, this kind of weld done before will not allow this one to this, because already welding done here makes this one rigid. So rigid structure prior to continuous seam weld, before you do continuous seam weld. So we call it is a tack welding. This is another way to minimize the distortion happen due to residual stress or thermal residual stress. Also, Another issue, have to select the condition, welding condition. This is one probably have to follow the International Welding Association where recommendations. There are many recommendations about the speed, amount of the filler, type of the filler to be used, must be compatible with the base material, and so on. Must be selected carefully based on the recommendation of the International Welding Association to reduce the distortion, also flux type, and so on. The proper part can be preheated. The base material can be preheated. Another solution or another way also, the base part can be preheated. Preheated mean we heat the base material before we do the welding. Why? To reduce the temperature gradient. Temperature gradient means that, or thermal, the temperature difference between, because the base material is cold. When you do heating and melting in the welding zone, this area become very hot and other material become cold, still cold, right? Then temperature gradient is very high and thermal residual stress will be very high also as well. If you heat the base material, then temperature gradient or the temperature difference between the parts will be less. This will leading to less thermal residual stress and also distortion. Stress relief. Stress relief after you finish the welding. After you finish the welding, when end, then you can do stress relief by heat treatment. You do heat treatment. What is the heat treatment? You heating the weld or the base material, all base material, you bring all material, you do heating, and then when you do heating up to a limit or recrystallization limit, all this kind of residual stress will be released. This one will make a relief to the residual stress. Proper design and weld melt, which is also have to follow the recommendation of the International Welding Association, as we described earlier in the previous chapter, which you have to use the weld joint, exactly follow the weld joint, weld type, and so on, based on what we described earlier in the previous chapter. This is a recommendation to reduce whatever we call is a residual stress and warping. What defect could happen in the welding? The defect, based on also International Welding Association, is a crack, cavity, solid inclusion, inspection, imperfect shape, and incomplete weld, incomplete vision, miscellaneous defects. This is the items or the type of the defect could happen in a welding. Let's see one by one. Let's see one by one. Let's start one by one and see this different type of defect. First is a crack. This is a crack. Actually, this crack, there are several type of crack, under bead and on bead and so on. This type of crack, it happen. This is transverse, this is longitude, this is longitudinal, this is transverse, this is underbeat. This is longitudinal, this is transverse, this is underbeat, and this kind of crack, it happened in the world due to high residual stress, as we described earlier or previously in the previous slide. So higher residual stress definitely will lead to this kind of crack type. And this one is very dangerous. We don't want that happen. We need to reduce. How to reduce? As we described in the previous slide, how to reduce the residual stress, to reduce the distortion, and even also crack. So fracture type, we call fracture type. This one, interpretation either in a weld or in the base material adjustment to the weld. This is a different type, serious defect. This one is serious, but because discontinuity, material here have discontinuity, this kind of opening. If you apply stress later, if this part taken and be used as a spare part for any, for machine or for whatever, and there are a stress here, if you apply stress here, this is the opening area, this one, propagation immediately will happen, and the fraction definitely will happen because discontinuity in the material significantly reduce the strength of this one, cause embrittlement, this definitely, or low ductility of the weld. This is also in general, this defect must be repaired, must be avoided, or must be also heat treatment. To heat treatment, heat treatment mean, as I told you, heating this one up to the critical limit and then very slow cooling down means that you release the residual stress and try could be reduced this kind of defect. This is the actual photo. Actually, you can see that this is actual here. Can you see? This is cracks in a welding. This is not good. This is not good. We have to avoid having this type of crack as we described as to reduce this kind. This is a traverse. This is a underbeat. This is a toe crack. This is longitudinal, this traverse and underbeat and so on. So this kind of crack must be avoided. Next is a cavity. Cavity is another defect could happen in a welding. And if you recognize that it is very similar to what happening or what we was discussing in casting, porosity shrinkage void. Casting? Yes, because here in a welding zone, this area in a welding area, here and here and here, we melt the material. When we melt, this is one melted and solidified. So we melt and solidify. Then it's like casting. Casting also we melting and solidify. So it is very similar to the casting. So porosity, small void, gases, small void in the weld metal formed because of the gases, gas trapped inside during solidification. Why someone will ask from where gases come? From several ways. From flux. You remember that we do welding either we shielding by flux or shielding by gas. So sometimes if you shielding by gas, gas trap inside and creates this kind of porosity, right? This one. Or if you shielding, if you're not using the recommended, if you're not using the recommended value when you do gas welding or you do flux welding, if you didn't use the correct flux matching or compatible, if you don't use the correct flux compatible with the weld type, this one definitely will lead to gas trapped inside and creating this kind of cavity. Also, if you use a I mean shielding gas, if you pump at a higher pressure or higher speed, it must be exactly follow the recommendation of International Association of Welding, then to avoid having this kind. So caused by inclusion also atmospheric gas, sulfuric weld metal, or surface contamination, also leading to the gas. It must be avoided while you do the welding. You must be carefully create a weld to avoid having this one. Shrinkage void is here. It also like casting. Then casting here, when you do casting, when you do melting and solidification, some shrinkage happen. This one could be avoided by adding the shell or might be designed well carefully to not having a bigger dimension to leading to the whatever we call shrinkage void. Yes, Abdullah, you would like to ask, I'm listening.
Doctor, on the welding, we will reach the melting temperature.
Excuse me again, your question, you will do what?
In the welding, we will reach the
Uh-huh.
melting. We will reach the melting temperature when
Will
we
what?
do reach the melting temperature.
Reach welding temperature. You
Melting.
will reach melting temperature, right? Yeah, exactly. You must reach melting temperature. How to weld? You must get liquid here. This material must be melted. Two base material must be melted in a welding zone. This must be liquid mix. So this one will be, we said that this is liquid, right? Do you remember that we describe in a welding? Welding is liquid, solid, and solid liquid. This is a different. This is a vision welding. In a vision welding, this is liquid, right?
Yes, but we say that we are not melting the temperature. We will reach. We will not reach the melting temperature. We will just weld by like do the heating, and we will not reach the melting temperature. That's what I
But
remember.
how to do welding if you don't reach melting temperature? How to be liquid? We said liquid. This is a liquid mix. Liquid means this one liquid, and then mix. So how to get liquid is unless you melt. Abdullah, you
Okay,
hearing
okay,
me?
yeah, it's clear
Yeah,
now.
yeah. This is liquid mean the two base material must be melted. This one must be liquid. This one in a welding zone, not all, not everywhere. Not, you're not going to melt all the part. We're going to melt here, only here in the welding zone. Then you get liquid, and you get liquid mix, and then probably added filler. We added filler also, so get liquid and added filler. Then unless you get liquid, you cannot just do welding, right? You agree? You must melt.
Yes, yes.
You must melt. We here we melting. In a vision welding, we melt the base material, right? Exactly.
Okay.
So this is the cavity it happened. Next is solid inclusion. Solid inclusion mean foreign material trapped inside the welding. We call it foreign inclusion. It most common form is a slag. Slag is slag is what is a slag? Flux is react whenever you when you do use a filler which is could be, for example, in arc welding is a stick itself and coated. I mean, flux could be coating, could be boring, could be tubular. It doesn't matter. But a flux, when you heat the filler, when you melt the filler, flux evaporated and react with the environment and creating slag. So slag is created. Slag supposed to be flow up. Slag created supposed to be flow up and create a layer on surface that what we remove. Sometime trap inside. In this case, if you don't use compatible flux, if you don't use compatible flux based on the welding association. So welding association make recommendation. If you welding steel, you have to use this flux. If you welding aluminum, another flux. If you welding copper, different type of flux. Then if you don't use the recommended flux, sometime flux trap inside and you get foreign inclusion. We call it is a solid inclusion. Definitely this is bad because this one reduce the strength of the weld. The weld, this kind of weld defect. Can you see that? So this is trapped inside. So this is definitely is a defect. We would like to avoid having this one. Then you have to follow recommendation. So also metallic oxide. Metallic oxide, it happen if you don't shield well. You know that we shielding by gas or shielding by flux. If you don't shield well, then some oxide will be created, and this oxide definitely will be, as you can see here, we call it is foreign material inside or inclusion. Then you get this one also reduce the strength of the material. We don't want to have harm. Then we need to shield perfectly. We must shield to avoid oxide solid inclusion in a material, which is a big defect, reducing the strength of the weld joint. Next is incomplete vision. Incomplete vision, as you can see here, the weld not completed. Can you see that? It must be completed, but not completed. In hurry, done in hurry. So the technician didn't complete the weld in the joint. The weld bead in wedge vision not occurs through the entire cross section of the joint. Several forms of incomplete like this. This is the actual photo. You can see that not completed here. He's in hurry, so he didn't I mean just give enough time. And filler also is not, he didn't added enough filler here to complete the weld in the, as you can see, the cross section here to cover all the cross section. Then definitely it's clear that the filler is not enough. Filler is less. Another one is weld profile. Weld profile, this is a good, this is a good weld profile. This is needed, this is desired, this is required. We would like to finally reach to this weld profile, but different defect could happen in a welder, like undercut, like underfill, like overfill. Overfill mean, well, the filler is too much, increase too much, then overfill. This is less. Filler is not added adequate. If filler added here, he can get underfill. This underbid has certain part of the workpiece evaporated, and somehow due to the welding. But this is kind of defect we should carefully design a weld to avoid having this different type of defect. This one is a good profile that required to be get. This is a defect in a welding. Inspection and testing method. Inspection, what is an inspection? Inspection, it means that to check the weld joint, to check the weld joint. Why? To be sure that the weld done, the weld quality is okay. You need to do inspection. Inspection means to check the weld joint. Later, after weld done, you need to check. We call it inspection. To be sure about the quality, to check the quality of the weld, whether the defect is there or not. There are a defect or not. If there are a defect, this weld is not okay. But if free of defect, then quality is good. So you need to check this one. We call it inspection and testing. We're going to discuss about visual inspection, non-destructive evaluation, and destructive testing. One by one, visual, as you can see, by using, technician can, see the inspection by seeing the weld done. So most widely used welding inspection method. This is first one. This is the first method, easy and first human inspection visually. You look to this, whatever we discussed earlier for the whether the envision completed, whether profile weld defect happen, whether there are a cavity, but definitely on the surface there are a cavity, there are a porosity, whatever defect that we described previously or previous slides, he checked visually. The technician check visually. Dimension, warping, distortion, crack, cavity, incomplete vision, and other surface defect. He checked visually, but this one limited to the surface. This one only limited to the surface defect. Welding inspection must also decide if additional tests needed or not, because sometime or some cases defect happen not in the surface but below the surface. So this one cannot be detected visually. This one cannot be detected visually. So visually can detect only whatever defect happened on the surface, only on the surface. Whatever happened below the surface, this one cannot be realized by visual inspection. We need to do another testing to understand whether this one defect, there are a defect below the surface or not. We have whatever we call non-destructive evaluation. The word non-destructive means we are not going to destroy the weld joint. Weld joint will remain okay. We'll not destroy it. We're using ultrasonic testing, we read radiographic testing, dye penetrant testing, and fluorescent testing, magnetic particle test. This is 4 tests as a non-destructive. Non-destructive means we're not going to destroy the test joint, right? First one is the ultrasonic. First one is the ultrasonic testing. Ultrasonic, we use an ultrasonic signal. Ultrasonic signal. This is a sensor, ultrasonic sensor, and detector as well. This is ultrasonic sensor and detector. Then this one emits the ultrasonic, and then ultrasonic return back again to detect it here. So this one mainly related to the speed of the signal. You send signal, go and back. So based on the speed here will be different in case we have or the signal facing some cavity or some defect below the surface. In this case, you get a peak, you get another peak, then they realize that this is one peak, this is one peak related to this one, this is another peak related to the other one. Then they can understand this is a signal, correct signal, because coming back, then the peak it's happened here, then we can realize that there are some defect located below the surface, so they can realize, and where exactly then they can realize whether there are a defect or not. They call it non-destructive. Why non-destructive? Because joint is okay, joint is same, no distortion, we didn't destroy the joint. The high frequency sound wave, ultrasound, high frequency sound wave, more than 20 kilohertz, usually through specimen. This one directed through specimen or emitted through specimen. So discontinuity, crack, inclusion, and so on can be detected as I just described. Then we can realize whether this one the free defect or there are. Definitely you can scan. You can scan the surface here. Scan everywhere so you can realize if there are any defect in below the surface, right? X-ray or radiographic testing. This one, you know that it's very similar to what the medical doctor using whenever someone or a patient go to the hospital to check whether there are a break in the bone or something. They do X-ray, then he can see whatever under the surface. So exactly we're doing that here. Radiographic testing or X-ray or gamma radiation. We put the part here and do X-rays, and if there are a cavity, can be detected as you can see here. So this is non-destructive because there are no thing happen to the welding joint. This one dipenetrant or fluorescent paint, and there are a spray here, as you can different type of spray. We apply this type of spray to the surface. This one will make, as you can see here, fluorescent make it. If there are a crack on the surface, this one will make it clear. But this one also subject to only micro cracks that you cannot detect by your eyes. Micro cracks that you cannot detect. So I mean, technician probably look to the surface and he find it perfect. And no, but there are a micro crack he didn't see by eyes. Then simply adding this or applying this spray on the surface, highlight this kind of, make it like fluorescent, make it clear. Then if there are a micro cracks on the surface or something, it will become clear, can be seen by eyes. So this is also limited, but however, this one is limited to the surface. You call it dipenetrant fluorescent pin, this one. It's non-destructive, and also another one is a magnetic particle testing. Magnetic particle testing here, this part is magnetic, apply magnetic field. You apply electricity, then magnetic field will be applied here. And this you put here, this is a ferromagnetic material. You put here ferromagnetic material powder. So here, bring here, for example, iron powder. Put iron powder here and then apply it magnetic field. Then iron powder will be distributed based on the magnetic field will be created. If distortion happen in the distribution of the iron powder, then you can realize that this distortion coming from the defect below the surface. This one cannot tell you exactly what located and how big, how small, however, can tell you there are as a defect or not. So this one can tell you, this is initial testing. Before X-ray and before the ultrasonic, this one in field, this one in the field, they usually use in the field to realize whether there are a defect in the welding or not. They call it is a magnetic particle testing one. If this one shows there are a defect here, probably you can apply ultrasonic or X-ray to get more information about the defect below the surface. Right, so this is a non-destructive. We call it non-destructive because you see in all this testing, we didn't destroy the weld joint. Next, we have destructive testing. Destructive means we are going to destroy the weld test or the weld joint. We're going to destroy the weld joint based on to do whatever we call mechanical testing or metallurgical testing. Mechanical testing like tensile test. When you do tensile test, then you destroy, fraction will happen to the weld joint. Metallurgical also, you need to cut to get the cross section. You need to cut the material so you can see under microscope, and you can put under the a different type of microscope. You can see the microstructure and so on. You need to cut the material, then you destroy the weld joint. Someone will ask me, you destroy the weld joint, then what that mean? Actually, it's kind of sample weld. If you do, for example, 100 weld, if you do 100 weld joints, then probably you take 2 or 3 to represent the whole welding. Then you can just pick up some sample of the weld and you apply whatever we call mechanical or metallurgical testing for some sample. And this one, you can consider this one representing the whole welding, the all welding, right? So this is kind of whatever we call destructive testing. Mechanical testing like tensile, we apply tensile test. We apply whatever fillet break test. We apply shear stress, test. You're applying shear stress here. You're applying here peel test. This is a peel test, shear test, tensile test. This is a fillet break test. Different type of test. In all kind of test here, you destroy the joint. You destroy the joint. This sample of joint will represent the whole, test or the whole joint that you apply or you produce. Weldability, actually weldability here, this one describe or concluding what we describe in chapter 25 and 26. Probably you read it and just go through. Next is a design consideration in the welding. Design consideration in the welding, there are some consideration you have to consider in a welding, like produce or product should be designed from the start as a weld, not casting, not forging. I mean, you need to apply, as we described earlier, probably you do fixation for the part to avoid thermal stress, probably you heating the base material, probably you make tack weld to make it rigid, and so on. Probably you have to follow the recommendation of the International Association, speed, what filler material you use, what electrode, what flux being used here with this weld, and so on. It must be carefully designed. Minimum part means that don't do many the weld for many part, only two. If you can just make it two part only at a time, it will be better. Don't make three, don't make four, because this one make it complicated. Definitely this one will lead to more defect. Try to limit the weld to the minimum part as you can. Good fit up part, good fit up. This one also you must follow the association recommendation when you prepare the weld. When you prepare the weld, I mean the joint for a weld and type of weld being used with this different joint. This one we call good fit up of the part. Assembly must allow access welding gun or welding machine. When you do the assembly, welding machine must be able to reach to the weld area perfectly. So this one should be carefully considered in preparation or design for welding. Design assembly should allow flat weld to be performed. Flat weld is easy, actually, more easy than other weld. So this is whatever we call flat weld. Priority is a flat weld. I'll show you. This is whatever we call flat weld. This is a priority. This is the horizontal, this is vertical, this is overhead. I mean, flat weld is the most easiest weld and less defect. So most easiest and less defect. No need for a highly skilled technician to do. This one is more difficult, as you can see. So if you can avoid having this one and can just make it flat weld, it will be better, easy, fast, and less defect compared with the other type of the weld. It's recommendation, I mean, in a welding recommendation. Low carbon steel sheet, if you're going to make a weld for low carbon steel, then low carbon steel, sheet, with a 3.2 millimeter, around 3 millimeter, then resistance spot welding probably is best choice based on the recommendation, actually. How additional strength and stiffness, this is based on the different type of material you added, probably filler material, probably flux material. This one provide you, this one is described actually as we earlier showed previously in the chapter here. In this chapter here, at the beginning of the chapter, we saw how this different filler material with alloys, actually we can add some metal alloys and filler and flux also can added strength and stiffness. Spot weld assembly, this is very important because this is machine provide active electrodes can be reached to the weld area. Sufficient overlap. Sufficient overlap mean here is the space, the distance between. You have to provide sufficient overlap, usually 1.5 the thickness. You must sufficient enough space here so weld could be done perfectly in this kind of welding process. Actually, this is the last slide in the chapter 26. This is the end of the welding process. Do you have generally, do you have any question? Generally, do you have any question in a welding? No question? Okay, if no question mean, uh, yeah, Zaid.
Doctor, the midterm will
Yes.
be open book or closed book?
Midterm, not yet decided. We didn't yet decide and we didn't discuss this matter yet. So soon we will announce. Soon, it is in 17. It's, I think, 2 weeks from now. I think this week, inshallah, we will announce by the end. I mean, next week, sorry. By the end of next week, we're going to announce the detail of the midterm, inshallah. I am not sure. We have to decide, all of us.
Is it a common exam or by doctor, by instructor?
Common. So every one of us are going to make one question, one
Okay, thank you.
numerical. Yeah, it's distributed among us. So this exam will be made by all of us. We have 6, I think, or 7, an instructor teaching the subjects, and everyone going to make a certain part, right? So it's common. Yeah.
Yes, thank you, doctor.
You're welcome. Okay, so material removal process. By the way, this chapter is very nice, very interesting, which is material removal process. Please, I hope you just get, it is really very important to focus on that. Chapter 17, 18, and chapter 19. I will start with chapter 17. Today I'm going to start with chapter 17, which is the theory of metal machining. Chapter 17, theory of metal machining. In this chapter, we're going to discuss about overview of machining technology, theory of a chip formation, force relationship with the Merchant circle equation, and circle power and energy cutting temperature. This is the items that we're going to cover in this chapter, chapter 17, right? Machining. What is the machining? Machining, as you can see here, we're removing a layer of material. Machining here, we're removing a layer of, this is a tool, this is a workpiece. This is a tool. In machining, we have a tool, we have a workpiece. There are a relative motion between a tool and workpiece. This workpiece, for example, is rotating. Tool is moving in linear or longitudinal direction. A part of material will be removed to reach to obtain the desired dimension, So this is the initial part. Later, when you cut, dimension will change, geometry will change. We call it shaping of the workpiece. So it is shaping process, as we described earlier, by removing part of the material. This is the machining, right? Machining actually, which is a material removal process or machining, there are a conventional machining, there are a abrasive machining, there are a non-traditional machining. We are going to focus here, in this subject on the conventional machining, turning, drilling, milling, and other related machining. This is the item that we're going to cover here in this subject, right? Later, probably in 406, we're going to describe the abrasive and non-traditional machining. If someone interesting to come to 406, we're going to cover about the grinding and the abrasive process and the non-traditional machining in 406, inshallah. Okay, so why machining? Why machining? Machining actually is very, very, very important process. Why? Why machining is very important? Because machining actually, this is, listen to me carefully. Listen, guys, listen to me carefully. Machining is the most accurate and precision shaping among all. Casting, powder, forming, and so on. Machining is the most accurate and precision process among all. Precision and accuracy can be obtained by machining, and machining sometimes follow other processes. Follow other process mean you do casting and then machining. You do forming and then machining. So even you do welding and maybe machining based on need, based on the need. If you really would like to get the precision and accuracy, machining is the way. So machining actually is very important because it provides excellent dimensional tolerance, external and internal geometry. So excellent, as I told you, excellent dimensional tolerance only can be done by machining. This is the only way to get the precision and accuracy. External and internal geometry can be done by machining. Surface finish, excellent surface finish can be done by machining. Remove of heat treat distortion. Distortion mean, as you can see in a welding, material will be distorted, get some material will be deformed and somehow, so machining can remove all this distortion. Economic for small quantity. And this one economic for small quantity. This is why machining is really important, right? Okay, limitation of machining or disadvantages. Disadvantage. Disadvantage of machining is that waste of material. Waste of material because you remove part of material. So some material will be removed as a chip, which is a kind of waste. Even compared with the other processes, the biggest waste of the material in the machining, because metal forming, there are no waste. Metal casting, there are no waste. Powder technology, no waste. Waste happen in machining. Because all part of material will be removed as a chip, time consuming because it takes time to do machining, it takes time, I can see. Energy also consumption because somehow big energy will be consumed in the machining process. Okay, machining constitute of three components. Generally, machining constitute of three components. Machining have a tool, workpiece, and machine. Tool, workpiece is a tool, this is a workpiece, and this is the machine. This is the machine. Machine here, functionality of the machine to hold the tool and workpiece, to provide the power and relative motion between tool and workpiece, so machining could be done. Then we have tool. This is the element, machining element, tool, workpiece, and machine. So tool, workpiece, and the machine functionality is to hold the workpiece and hold the tool and provide or deliver the relative motion between tool and workpiece and enough power to cut the workpiece material or to perform the machining operation. This is a machining process. Right. Machining is performed after sometimes stand alone. It could be stand alone. It could be done after manufacturing the other manufacturing process. As I told you, after casting, forging, and other process, because here this one can be done after one to provide the accuracy and the precision. Other process create general shape. Other processes create general shape, like casting, for example, creates a general shape. Shape be done, but casting cannot provide accuracy and precision. Why? Because in a casting you melt the material while shrinkage geometry will getting smaller. So initially we added whatever we call is a machining allowance. Machining allowance meaning oversized. As we described earlier in a casting process, we added whatever we call machining allowance. Machining allowance we added as a bigger size. We make it as a pattern oversized. So later when shrinkage happens, still dimension will be bigger. then you need to do machining. You need to also clean the surface because mix between sand and liquid and so on, then surface must be removed. So machining required after the other process. So other process generally creates a shape. Machining here provide the final shape, dimension, accuracy, precision, finishing, good surface quality, and so on. Right. In machining or in cutting, we call it machining or cutting. We have whatever we call single point cutting tool. This one we call it is a single point cutting tool. This whatever we call is a multiple point cutting tool. Single point cutting tool, it means that there are one point in a cutting. There are only point in the cutting. Engaged in the cutting all time. This is only one point. This is the only cutting point. This cutting point engaged in the cutting all time. This one have multiple point. Can you see that? This is multiple. 1, 2, 3, 4, 5, 6. So this one is rotating while this one is rotating. This is the edge. We call it is the cutting edge. The edge is come to the cut and exit, and then another edge come to the cut, exit, and another, and so on. So we have single point cutting tool, like whatever happening in a turning. So only one point engaged in the cutting all time, or we have multiple cutting edge tool. We have several cutting edge, and these several cutting edge, then all are cutting in one cycle, but subsequently, one after each other. You can see that. You can see that here is showing that this is a single point cutting tool. Single point cutting tool meaning only one point engaged in the cutting, only one point engaged in cutting from beginning to the end, all time from beginning to the end. A single point cutting tool. This is multiple point. Multiple point here, you see that multiple edge, multiple points. This is one coming and move out, another one coming and move out, another one coming and move out. We call it as a multiple edges. This is a different type of machining, either single point or multiple point cutting edge. Right. Here is a process. Let's take the lathe or turning operation, whatever we call. What is a three fundamental machining parameter? There are whatever we call is the three fundamental machining parameters. The three fundamental machining parameters, this is a tool, this is a workpiece. The tool now engaged in the cutting, tool engaged in the cutting to remove a layer of the material. Then the relative motion between tool and workpiece must be done. There must be relative motion, must be applied relative motion between and workpiece. Otherwise, if no relative motion between tool and workpiece, then probably cut will not be performed, right? Definitely time is almost finished now. I have to actually stop here, and we'll continue discussion about that next time, inshallah.